So we have been doing Bernoulli's theorem application, right?
Yes, sir. Yes.
Should we continue that now?
Sir.
So Bernoulli's theorem says that if you say what was Bernoulli's theorem, it is actually the pressure sum of pressure plus kinetic energy half rho v square per unit volume plus potential energy rho gs, that is per unit volume, always remains constant. Okay.
Okay, sir.
So one application venturimeter we have discussed. Another you can say here, let's suppose we have horizontal flow. If that is if fluid is flowing horizontally like this, might be some different area of cross section. It can go like the area of cross section might change, but it is horizontal only. That means the fluid is traveling like this. Here area is A1, and here in this short tube, let's say area is A2. Density is rho. Here the speed is V1 and here the speed is V2. So if I ask to use this principle here, so you can say that at this point, if I say pressure is P1 and at this point pressure is P2. So what we write, P1 plus half rho V1 square. And height, if I take this is the reference frame. So what you observe that height here also is h and height here also is h. So height there is no change. Even if you write the height, that will be rho gh here also, and the second here also I can say it is pressure is different, P2 plus half rho V2 square plus rho gh gets cancelled because height is same at both points. So what we get here, it is P1 minus P2 is equals to half rho V2 square minus V1 square. Okay.
Okay. Okay.
Whatever I'm writing, you also write the notes and after the class you send. Okay, Neil?
Okay, sir. One second.
Okay. No, this is not done right now. Okay, whatever is there, first you write. Done?
Yes, sir. One second.
Okay.
Yes, sir. Done.
Okay. So here you can observe one thing that left side is P1 minus P2, right side is V2 square minus V1 square. So that means if I can say if P1 is greater than P2, so if this will be positive, but this will be positive, then this side V2 will be greater than V1. So if P1 is greater than P2, then V1 is less than V2. It means that uh, where velocity is more, if velocity is more, the pressure is less. You can see because this side is P1 is greater, this side V2 is greater. So you can say that pressure decreases. Pressure decreases with increase in velocity. Pressure decreases with increase in velocity. Understood this point, Neil?
Yes, sir. Understood.
If I take an example of like airlift, when the how the aeroplane gets the lift. So what happens? You see the wings of the aeroplane is slightly curved at the top like this, slightly curved. And if the air is moving, if air is flowing like this, so you see that the air that will go down, it has to travel less distance. But due to curved part, the air that will go to the top of the plane has to travel more distance. Are you understanding my point?
Yes, sir. I'm understanding.
So this lower part air has to travel less distance and they should reach from this part to this part in the same time. So here the speed is less, but here the speed is more. Okay, V2 is more than V. That means we can say the speed of air above the wings of plane is greater than that below the plane, below the wings, below the wings. And due to change in pressure, this concept we can apply, which says that if V2 is greater than V1, then P1 will be greater. So if I say here the pressure on the plane is P1, and from the top part, let's suppose here the pressure on the plane is P2, then which will be greater, Anil, P1 or P2?
Yes. P1 speed will be greater because the on pressure on P2 will be more. So
P1
because the
is
plane
greater.
will upwards.
What are you saying? Press when the P1 or P2, which will be greater?
P2 will be greater.
Why?
Basically because yeah, the shape of the wing on the top is different. The distance to cover is more. So the pressure technically will be more only on the P2.
Okay. Did you write the notes properly?
Yes, yes.
Okay. Now see this line and tell me where the pressure will be more.
P1.
P1, because V2 is more than V1. Here I say that on the top of the wing, speed is more. Here V2 is more than V1. So if V2 is more than V1, then I written here P1 will be greater than P2. So the upward pressure on the plane will be more. That's why the plane goes up in the sky. And while moving horizontally, it remains flat due to its own weight. Plane does not come down. Why? Because there is a net upward force acting on the plane which balances its weight, and that's why it can fly horizontally in the sky. Understood?
Understood.
So we can say that net upward force on the plane balances the weight of plane, and hence it can fly horizontally in the sky. Please write this, Neil, and understand also.
Sorry. Sir, done.
So you understand why the net upward force is acting on the plane?
Yes, sir.
Okay, can you explain in short why the plane is balanced when it is flying horizontally in the sky? In your own words.
Basically, the pressure of P1, which is lower than the wing, is greater than the pressure of P2, which is above the wing. When pressure is less, then the velocity is more. So the air on top, the air, its velocity is higher, which and उसके नीचे का is lower, which causes an upward force on the plane, which causes it to float. And then speed maintain करने के लिए engine चाहिए. तो ऐसे therefore the plane is able to stabilize itself and float in the sky.
Correct. Good. So that was one application of Bernoulli's theorem, that we understand how the plane can balance itself in the sky. Okay.
Hmm. Oh,
One application we will discuss of that we say as Torricelli's theorem. Let's suppose you have a tank, a large tank, and here you have kept a small hole. This is the some liquid that you have filled here in this tank. The tank is kept on a surface, and from this orifice here, one any liquid is coming out. This liquid is coming. If I say this total height of the tank is capital H, and the height of this orifice is H. Height of the orifice is H. The density of the liquid is rho. This area of cross section of the tank, capital A, is quite large as compared to the area of the cross section here, A. So capital A is far, far greater than. So what we understand from the principle of continuity, that is A1 V1 is equal to A2 V2, and it says that the A1 by A2 ratio is actually V2 by V1 ratio. It means it is inverse type of ratio. This side is A1 by A2, this side is V1 by V2 by V1. So it proves that if area is more, speed will be less. So here area is far, far greater. So speed will be far, far less. So we can assume that here the liquid is at rest. Here there is no speed. Liquid at rest because the area is greater. So you can take speed as rest. Whereas here it is coming out with some speed V. I assume when the liquid that is coming out, that level I'll assume as a reference line. This I'll take as the reference line. That means here there is no potential energy if I take reference line. Now at this point, we take the pressure that is outside the above the liquid, that we take pressure is atmospheric, P atmospheric. I know that in Bernoulli's theorem, P plus rho G H plus half rho V square always remains constant. So this equation I will apply applying Bernoulli's theorem, at top. Okay, this point also you can imagine this point is M, and here just outside this point is N. At top point M and just outside the orifice, that is N. So at M, pressure is P atmospheric, P atmospheric plus the height, potential energy height, the height above the reference line. This height I'll take height above the reference line, and that is H. So rho g h, there is no speed there. So kinetic energy is zero because I have written the particles are at rest at the top. Just outside, this is also atmosphere only. So pressure will be again here P atmospheric, and there is no potential energy here because this is the reference line, and kinetic energy will be half rho v. P atm cancel, this 0 0 also cancel. So what we get here is rho gh is equal to half rho v square. Rho you can cancel. So we get here gh equals to v square by 2. That is v square equals to 2gh. So v will be under root 2g. That means the liquid is coming out of the hole with this speed, and that's why this is called as velocity of efflux. Velocity of efflux. Understood, Neil?
Yes, sir, understood.
Please write it properly, step by step, and understand. Okay, you can take your time, no problem, but you understand each and every step.
Yes, sir. Done.
Okay. Do you understand this?
Yes, sir. I understood.
So you see, this speed, you remember that if a particle is falls freely, that means particle is dropped, no any noise in its speed from some height h to the ground. Then when it strikes the ground, then the formula of speed we find v square equals to u square plus 2gh. U is 0, so v is under root 2gh. And what you find here that if I take some tank here and I make an orifice here at the depth h, then the liquid that is coming out from this orifice, and that they also have the same speed, v equals to under root 2. So the bottom line is the liquid coming out of the orifice is just like a particle dropped freely from the same height. Do you understand this line, Anil?
Yes, sir.
So the liquid, let's write it here down. The liquid coming out of a small hole, coming out of a small hole in a large tank, in a large tank is like a or is equal to, is the liquid coming out of a large small hole in a large tank is equivalent to, a particle falling down freely from same height. They both are same. Both will have same. They both will have same velocity. This is called as Torricelli's theorem. Torricelli's theorem. Please write this statement, Neil, and compare by these two diagrams.
Yes, sir, done.
Okay. So now we know that if we have a tank here and tank here and we keep in orifice a small hole here from which liquid is coming out. Let's suppose this is the liquid. Density rho, height of liquid is h, height of the orifice is, depth of the orifice is h. Now the liquid that is coming out with some velocity v that you have found is under root 2gh. It will fall at some place on the ground like this. So this is called actually range. Okay, we write as r, where it is falling. So it is like a horizontal projectile. We know that in horizontal projectile, what happens if any body is thrown horizontally from some height, from this some height, let's suppose is h naught with a speed v, then it falls on the ground like this. And this range we find as the speed multiplied time of flight. And time of flight depends upon how much height is there. If height is h naught, we write is 2 h naught by g. So here also, if I try to find nil range of liquid, that means at how distance from the container it is falling on the ground. This is the range. So range we can find as the speed, that is v, and the time we have to find how much height it has to come. So the complete height was h, this height was small h. So this will be capital H minus small h. Understood, Neil?
Yes, sir, understood.
So this will be 2 capital H minus small h by g. And v itself you have already found, v equals to under root 2gh. So this I can write under root 2gh times 2 times capital H minus small h by g. Both are in the square root, so we can take combine. This is 2gh multiplied by 2 capital H minus small h by g. I think g cancel. 2 you can take outside because there are two twos. So 2 multiplied by h into h minus h. So this is the formula for the range at how far they will go, that you understand. So right up to here, Neil.
Okay, one second. Yes, sir, done.
Now, so this is the range. If you are interested, Neil, to find the maximum range for range to be maximum. So this h should be equal to h minus h. That means 2h should be h. So h will be half of h. It means that the orifice should be exactly at the midpoint of the height above the ground. If the height is h, then the orifice should be exactly at the midpoint here. In that case, if this I'll write as small h, that is equal to h by 2, then the liquid will go to the maximum range. And if I try to find the maximum range, then this is 2. Both are equal. This is also h by 2. This will be also h by 2. So you get here 2 times h by 2, that is h only. That means in that case, the maximum range is equal to height above the cloud. That is the maximum range condition and the maximum range value. This also you add in this previous line, whatever you have written. Okay.
Yes, sir.
Hmm.
Yes, sir. Done.
Okay.
Okay.
Now, if I take one example, this is a very good example. Let's suppose I have a container in which I have kept two types of liquids. One liquid you can see at the top here, that is having density rho 1. Other liquid you can see here at the this part, and it has a density rho 2. This liquid has a height h1, and this liquid has a height h2. It is kept on the ground itself. And we have an orifice here, just near the bottom of the container, from where liquid is coming out, and we have to find its speed of efflux. That means with what speed the liquid will come out. Process is very similar. You try to use the Bernoulli's theorem here. At the top, you can see this area is very, very large. So the liquid remains at rest. So if I take a point here, M, and just outside here, I take as M, N, and I try to apply the Bernoulli's theorem, applying Bernoulli's theorem at M and N. So at the M, here only pressure is atmospheric because this is out uh, top side of the liquid, and the orifice height is h1 plus h2, so you can write. But here you can see there are two liquids. This is rho 1. Rho 1 is up to height h1 only. Rho 2 is height of h2. So pressure energy you have to write separately. Rho 1 g h1 plus rho 2 g h2, because rho 1 is different, rho 2 is different. And it is at rest, so kinetic energy will be 0. And when outside here also, it is just outside the orifice, means this side is also air. So pressure will be atmospheric. No potential, because this we call as the reference line. And kinetic. Now, which liquid is coming out? Rho 1 or rho 2? So rho 2 is coming out. Okay, rho 2 is down, it is coming out. So kinetic energy will be with rho 2 only. Half rho 2 V square. P atmospheric you can cancel, 0, 0 also you can cancel. So what you get here, rho 1 G H1 plus rho 2 G H2 is equal to half rho 2 V square. Here you can take 2G common, this side is H1 H1 plus no, I think rho will be also there now. Rho 1 H1 plus rho 2 H2 is equal to, this side is rho 2 V square. That means in this case, V square will be 2g into rho 1 h1 plus rho 2 h2 divided by rho 2. In case of two liquids, how to find the speed of flux? Very important concept. 2g rho 1 h1 plus rho 2 h2 divided by rho. That is the speed of flux. First, tell me, Neil, you understood?
Yes, sir. Just 1 second.
Yeah.
Yes, sir. Understood.
Okay. Please copy it.
Yes, sir. Done.
Okay, so today we have completed the Bernoulli's theorem and its application. So you understand the Bernoulli's theorem is all about conservation of energy, right?
Yes, sir. Yes, sir.
And also you can say that it is basically uh, energy per unit mass or per unit volume. And there are a lot of application like venturimeter we have discussed in the last class. Today we have discussed the aeroplane concept, how the aeroplane can balance its weight because the pressure below the plane is more as compared to the pressure at above the plane. So there is a net, always a net upward force acting on the plane, which can balance its weight, right?
Right, right.
And then this if a large tank is there, then and a small hole, a small orifice is there from which water or liquid is coming, what should be its speed? There also we have seen that the speed is very much equivalent to a particle dropped from some height h. It will also speed under root 2 gh, and there also we are getting the under root 2 gh. This is Terrestrialist theorem. And then we discuss if there are two liquids, then also how we can find the speed of the flux. Okay.
Hmm. Okay. Okay.
So next class we discuss about the other properties like viscosity, surface tension. Okay.
Okay, sir. Sure.
Okay. Bye.
Bye, sir.